The very last topic we will cover before we begin considering life elsewhere in the universe away from Earth is going to concern the very first origin of life on Earth. When did you go from non living chemistry to living biology? Now, as we discussed earlier, without a really robust definition of what is life, it's hard to really think about how did we go from non living to living. It seems kind of vague. But to help us think about this question, in 1952, there was an experiment conducted where some fairly simple gases, molecular hydrogen is a gas of two hydrogen atoms, water vapor is a gas of three atoms, two hydrogen atoms plus an oxygen, plus ammonia and methane. Methane was the most complicated gas in this experiment. Methane contains five atoms. So none of the gases in this experiment were particularly complex. They weren't like those giant amino acids and proteins we talked about earlier in the course that have hundreds of atoms in them. So these scientists took these very simple gases, they put these gases in a sealed chamber, and these were the gases that were believed to be present in the Earth in the Earth's atmosphere right after the Earth is formed. And with the gases in a sealed chamber, these gases were exposed to electrical sparks. These electrical sparks were to simulate lightning and lightning strikes that occurred on the early Earth. So you have a chamber with some simple gases. You allow those gases to be exposed to electrical discharges. And let's see what is produced when this experiment is allowed to run. And after a while, this experiment produced complicated amino acids and other complex organic molecules. So from some very simple building blocks, these four gases, and exposed to an energy source, you could produce the complicated amino acids and other complicated organic molecules that we talked about earlier in this course. Now, this experiment was later on followed up in a different way. What if we take the electrodes that provide an energy source, and what if we replace them with a hot plate or some heat source? Maybe instead of lightning, we want to simulate molten lava or something that was really hot. The early Earth was incredibly hot, had a molten surface. What would that produce? So if you take the gases that were believed to be present in the early Earth's atmosphere and expose it to a heat source, or maybe we could expose it to a UV source. The early Earth's atmosphere had no ozone layer, so UV light from the sun could reach the surface of the Earth. UV light could react with these molecules and cause them to recombine. Also, what if we changed the content of the gases? Later on, the scientific consensus of the chemical content of the Earth's early atmosphere was updated. The experiment was repeated again, this time with a different mixture of gases, with the updated of what we believe the early Earth's atmosphere was like. And in all of these experiments, it was found that these complicated organic molecules, these amino acids, were always going to be produced. Now, obviously, some of these experiments produced more amino acids than others, but the profound consequence of the Stanley Miller and Harold Urey experiment was that by exposing some very simple gases that were present in the early Earth's environment to an energy source, you could take these very simple molecules and build through a fairly generic setup some of the very complicated amino acids that are the foundation for all living things on Earth. So the Miller-Urey experiment demonstrated that common energy sources can cause the formation of complex organic molecules, and these all mix together in a type of primordial soup. Now, these amino acids, these other organic molecules, are the basis of what combines to form a wide variety of complicated organic molecules and eventually life. So these complex organic molecules can form under a wide variety of conditions. And this has a very profound consequence for considering life elsewhere in the universe. It wasn't that you only form complex organic molecules in one experiment. You could alter the content of the gases, you could alter the source of your energy, whether it's a heat source or UV light or lightning strikes. In all of these cases, you are still creating amino acids that form the building blocks of life. And so this suggests very strongly that planets with different starting initial conditions, planets with different atmospheres right after formation, still have a very strong chance of forming these amino acids. And if you could form these amino acids, then you could form more complicated molecules and proteins and potentially have the life arise on that planet. Now, very similar to natural selection of living organisms that we discussed earlier, these molecules were in some type of environment, and these molecules would interact with their environment. And some complex molecules would be preferenced and do better, i.e., not be broken apart by their environment, while some other molecules would be broken apart by their environment. So, in a way, there is also going to be a type of chemical natural selection of these complicated organic molecules when they're exposed to their environment. So, molecules will be going around in this primordial soup. They'll be bonding together, they'll be separating when they are broken apart for various reasons. More strongly bonded molecules are going to resist being broken apart. So this chemical natural selection, this chemical evolution would tend to concentrate and condense the more stable molecules in a certain area. And these more stable molecules could then bind with others to make even bigger molecules. And eventually you would find a molecule forms with the unique property that it could make copies of itself. So chemistry is becoming biology. Now, if we say chemistry, we are thinking non-living combinations of atoms that form molecules. Those molecules could be pretty complex. If we are talking biology, we are thinking living things. So where do you draw the line? When does something go from non-living to living? Well, that's a very deep and involved question. We discussed earlier in this course that we don't really have a profound or robust definition of what does it mean to be alive. So I am going to offer, and I'm going to say this with the caveat that I am absolutely not trained in biology, so just take it for what's worth, that perhaps that's just the wrong question to ask. Maybe we shouldn't worry about when does non-living become living. Perhaps going from non-living to living is more like a spectrum, more like a gradual, incremental thing, not just a very discrete, you're not alive or you're alive and there's no in between. And again, I say that as someone who is absolutely not trained in biology or chemistry. That is just what I want to offer. Personally, my favorite definition of what is life comes from Erwin Schrödinger's definition of entropy. But again, like I want to emphasize, I'm not a biologist, so if you want a better definition of what is life, go to a biologist. Life is believed to have originated in shallow tidal pools that contain these complex organic molecules on Earth. The original source of energy in these shallow tidal pools might have been lava or lightning or UV light, but that is far from certain. A contrary hypothesis for this is that life might have originated in the ocean near some hydrothermal vents. These hydrothermal vents spew out complex organic molecules, and they are warmed by magma under the surface, under the crust in the ocean. And this might have been the original source of life on Earth. So life is believed to have originated in shallow tidal pools, but that's far from certain. An even more exciting hypothesis is that life might have originated elsewhere in the universe and spread across on another planet, like Mars perhaps, but then an asteroid might have collided with Mars, kicked up some debris. That debris could have been traveling around the sun. Remember, during the period of heavy bombardment in the early solar system, there was a lot of stuff crashing into all the planets, and life might have been a stowaway on a meteor that eventually landed on Earth and found the conditions on Earth amenable to life. So this is just one hypothesis. It is possibly the least likely, but it is also obviously one of the most exciting. So watch these two videos, Neil deGrasse Tyson talking about water on Mars and extremophiles, and What Are You by Kyrgyzak, and I will see you in the next video.